A warm welcome to everyone to the 21st session of the GO2NE Global Ocean Oxygen Network webinar series. I am Damodar Shenoy from the CSIR-National Institute of Oceanography in Goa, India. And the whole GO2NE team is very happy that you took your time out to be with us and with the incredible speakers this morning, afternoon, evening. Before starting, we would like to bring to your attention to the Ocean Deoxygenation newsletter. Good news, with the new issue which is out this week and can be accessed via the QR code. If you are on Twitter, you can follow us at good_ocean_oxy for the latest news and the activities of the GO2NE community. The next GO2NE webinar will be in September, so please look out for the details to register when the webinar is announced. Some quick housekeeping announcement before welcoming our speakers. You as attendees can pose your questions to the speakers by typing in the question and answers Q&A box. The chat box area can also be used to share additional information if you have any logistical issues. So let's get started now. Let me introduce our first speaker. He is Dr. Sudheesh Valliyodan, who is a young and dynamic researcher working presently at the Central University of Kerala, a state on the west coast of India. Sudheesh did his master's in hydrochemistry and later his PhD in marine sciences from the Cochin University of Science and Technology. His research interest spans oxygen minimum zones, greenhouse gases, marine biogeochemistry, plankton ecology, and ocean acidification. He has 25 research papers to his credit, and today he is going to talk to us on oxygen minimum zone dynamics of the Eastern Arabian Sea. Over to you, Sudheesh. Yeah, your slides are visible. Please go to the full screen mode. Yeah, perfect. Please carry on. Sudheesh, please unmute and start again. Perfect.
Thank you. Sorry. Good morning, good afternoon, and good evening to all wherever you are. I'm very happy to be here to present or to give a lecture, the talk on the oxygen minimum zone of Eastern Arabian Sea. And today I will mostly talk about some observational data set. All my research is focused on observational data set and collected as a part of marine ecosystem dynamics of Eastern Arabian Sea project. Then I was in Center for Marine Resources and Ecology. And we know oxygen minimum zone everywhere in the world ocean we can see. We can see the perennial oxygen minimum zone that occurs between 100 and 150, 1,500 meters in the open ocean region, in equatorial Pacific, Indian Ocean, Atlantic, almost every ocean we can see. But its intensity, the intensity of oxygen concentration vary with respect to various reasons. So it maybe depends on the productivity patterns, dynamics, and many other factors over the region. And Arabian Sea, that is my one of the most intense oxygen minimum zone generally we see. We have seen many different stories about the Arabian Sea and the Arabian Sea OMZ. And if you see the oxygen minimum zone of Eastern Arabian Sea, generally there is a eastward shift and the maintenance of oxygen minimum zone in the eastern part rather than a productive zone of Arabian Sea. That means the most productive part of Arabian Sea generally we are seeing at the western side instead of but underneath of that particular water volume we are not seeing an intensified oxygen minimum zone. So but in Arabian Sea there is a eastward shift of this oxygen minimum zone, though the eastward region is not that much productive compared to the western region. So most of the potential researchers, those who are working on just the oxygen minimum zone or those who are working on the oxygen cycling, they are interested in the eastern part. And if you see the bioargo floats, that is one of the most modern equipments that there we will get the oxygen concentration of the water volume. And if you see the bioargo floats, the status of bioargo floats in the Arabian Sea, you can see the eastern part of Arabian Sea. That means the west coast of India. There is the completely devoid of this bioargo floats. So what will happen because of that? And we know much of our data presented in the World Ocean Atlas are coming from this World Ocean Atlas data or any other data sourced from different observations. So if you see in the in the right panel, you can see the monthly distribution of oxygen along the eastern Arabian Sea. You can see the right-hand panel, it is collected from the World Ocean Atlas, recently from 2018 World Ocean Atlas data. You can see the 20 micromole as well as the 5 micromole contour. That is the 20 micromole we generally considered as oxygen minimum zone layer, and the 5 micromole considered as its core, where the denitrification generally take place. So the 20 micromole concentration we can see very nicely depicted. And the left-hand panel, you can see that is from observation, the monthly observation we conducted as a part of MIDAS program of Ministry of Earth Sciences. You can see the 20 micromole contours in both the panel, mostly matching. But if you see the 5 micromole oxygen concentration, that means the core of oxygen minimum zone of Eastern Arabian Sea that is not well depicted in the World Ocean Atlas dataset. That is mainly because of the devoid of oxygen data sets that is being considered for the World Ocean Atlas. So we need to look more on the eastern part, and we are talking about the intensification or the maintenance of an intensified oxygen minimum zone in the eastern part. So we need to be more cautious while using the, or those who are interested in working in the eastern part, we need to be more cautious while taking the World Ocean climatology data. So if you see our location where we collected those data sets, this is the different station locations we collected on a monthly basis for an year from around 22° north to 8° north. So you can see the distribution of oxygen profiles from north to south. That means from around 8° or the 6° to around 21°. If you see the 6°, 6.5°, the first figure from the top left panel, you can see the oxygen minimum zone, the zone at which the oxygen concentration has the 20 micromole oxygen layers. That is situated between 100 to around 650. So if you see the after like north of like around 10°. So we are seeing there's a deepening of OMZ. That means there's the deepening of OMZ. The 20 micromole layer will be seeing up to near 800. If you go again further north, you can see it deepened again, and we are seeing up to 900. Then if you see on the northern part, we are seeing the oxygen minimum layer up to 1350. That means around something you can see from north to south. That means from 8° to 22° itself, you can see a lot of difference in the depth of or the thickness of oxygen minimum zone from around 650 to almost double, around the 1400. That means there is a large difference within a span of around 14°. There is a span of the thickness of OMZ is almost doubled. So if you see again the distribution pattern from around 6° to 21°, the section, you can see again the core OMZ and the oxygen minimum zone. The oxygen minimum zone considered as 20 micromole, and the core OMZ considered as 5 micromole oxygen. Where in the core oxygen minimum zone, mostly the denitrification takes place. So if you see the January, February, March, and May, and that is mostly the non-monsoon season or the before monsoon, you can see the 5 micromole contour extended up to around 12 degree north. And when the monsoon starts, the monsoon intensify June, July, August, or up to September, you can see the 5 micromole oxygen minimum contours started retrieving back to the northern part. That means it is restricted in September. By September, the core OMZ restricted up to 5 the 15 degree north. That means, and again after retrieval of monsoon, and you can see the 5 micromole contour again started picking up and extending up to 12 degree north. That means we generally considered as the monsoon month as the most productive period, but still we are not seeing that an intensification. That is what we are expecting generally because of the high production. We are expecting an intensification in the bottom layers. So one should expect an intensification of this oxygen minimum layer in the bottom waters or the mid depth, but we are not seeing in case of Eastern Arabian Sea. So what we are seeing, there is a oxygenation. That means there's a oxygenation of this oxygen minimum zone layers. That means through, if you see this figure, June to September, you can see in the intermediate depth, an oxygenated water is transporting from south around 6 degree to around to the 12 degree north. That means there's a oxygenation during the monsoon period. Because of this oxygenation, two things are happening. The monsoon induced changes, the monsoon induced remineralization, or the monsoon induced oxygen utilization, we are not seeing in the mid depth. Instead, we are seeing an oxygenation. And you can see that because of that, the 5 micromole contours is restricting up to 15 degree north instead of, that means there's a clear oscillation of this core OMZ between 12 and 15 degree between the monsoon and non-monsoon season. Then we have seen how much it is being constant or the ventilated. So you can see the color plot, that is during the monsoon time. You can see there is a clear increase of oxygen concentration between 150 to 500 meters. That is the core in OMZ. And again, when we talk about seasonality, it is not only the horizontal variability, but also there is a vertical variability as well because of the upwelling process. So during the monsoon month, there is a horizontal movement or there is a oscillation of intermediate oxygen minimum zone between in the intermediate layer. At the same time, this upper OMZ or the oxygen minimum zone is vertically extending because of the upwelling. So but this upwelling induced changes, you can see there is a large variation in oxygen across the Eastern Arabian Sea. You can see an intense oxygen minimum. That means the dissolved oxygen in the upper oxygen. When we take the average of oxygen concentration in the upper 100 meter, you can see during the around in the Central Eastern Arabian Sea, for example, 14 degree north, and those region has a intensified oxygen minimum zone, or that means the upper 100 meter, the average of upper 100 meter water column, it will reach up to 40 micromole. That means it will badly affect the fishery or the higher trophic organisms that we can expect. Apart from the open ocean dynamics, you can see a intensification, or you can see an oscillation of this oxygen minimum zone towards, or there is an intrusion of this oxygen minimum zone towards the coastal as well. Earlier we talked about the open ocean dynamics, mostly the horizontal and vertical, and also horizontally it is transported to the shelf region. That means when the monsoon upwelling started, this bottom oxygen water, the intermediate oxygen minimum layer is also transported to the shelf region, and thereby it poison the the nearby the shelf biogeochemistry also poison the oxygen minimum wherever whatever the water is transported from the coastal, the offshore regions to coastal, it again poison, and we generally seen the oxygen minimum, sometimes even anoxic condition or sulfuric condition. That also this oxygen minimum or the intensified oxygen minimum layer we are seeing only, or the oxygen, the sulfuric condition we generally see restricted only in the Central Eastern Arabian Sea. So when we talk about the intensification only in the Central Arabian Sea, we saw it is nothing related to an intensification of fertilizer runoff or anything, but we see it is mostly depends on the source water characteristics of the characteristics of upwelled waters. That means the central region of Eastern Arabian Sea is mostly very intensified in character. So those intensified oxygen minimum zone, because of the high upwelling intensity, it is transported to the central part, and it is modified because of the self biogeochemistry and forming hypoxic or sulfadic in nature. At the same time, because of that sulfadic nature, the entire bottom waters, the figure, the distribution plot we are seeing, the bottom oxygen minimum, the bottom oxygen concentration, you can see the fish community are escaped from the bottom layer, and it is segregated or it accumulated in the surface layer, and thereby it transported or it trapped in the waves and transported to the shelf or the coastal or shore region. And we are seeing fish kill in this Central Eastern Arabian Sea frequently during the monsoon period. And it is not only the fish community, but also the Bandi community also badly affected because of the low oxygen deficiency during, that means the seasonally deficient low oxygen waters. Also, it is not only oxygen, but also the environmental is seasonally acidifying as well. So generally we are seeing, or this region is mostly get attention for the oxygen or deoxygenation or seasonally anoxic or hypoxic during this monsoon period. But at the same time, it is not only oxygen, it is also the seasonally and acidifying environment. So one should expect a multiple stress during the monsoon month and acidifying on the hypoxic environment we can expect in this region, and that may also vulnerable or go intensify in future because of the climate related aspect. And because of this low oxygen, it is not only affecting the biology, it is also affecting the biogeochemistry as well. We are seeing a very intense greenhouse gas efflux during the monsoon period. You can see the nitrous oxide and the carbon dioxide level increasing like anything during the monsoon month because of the this seasonally anoxic environment. The denitrification is one of the major threat we are seeing in this environment. At the same time, we are seeing very high efflux of PCO2 as well. And when you can see the budget, you can see from the central region, because of the high intensified or the hypoxic environment, we are seeing very intense greenhouse gas production from the Central Arabian Sea. And to monitor this in future, how this system is modifying, we need to do more and more observations. And when we consider in the entire Arabian Sea, you can see until now there was no intensification up to the 15-degree north, but on the north of 15 degree, there are already an intensification of oxygen minimum zone is reported. But the decrease in oxygen levels are reported to be very, very low. And to tackle or to see the intensification of OMZ, we need more field observation rather than or we need more field observation using most modern sensors like stocks. And with this, I will stop here, and I will thank you.
Sudheesh, Thank you for the wonderful and interesting talk. We do have some time, so we have enough time with us. Let me just check out what we have in our question and answers box. There is one question which has been posed by Sushant Nayak. He wants to know, is there any ventilation with respect to oxygenated waters below a water depth of 500 meters?
Yes, we are seeing that. If you see this figure, you're remembering, you can see the ventilation up to 600 to 700 meters. But why I concentrated only the between 500 and 150? There we are generally seeing the most the intense part, and that region you can see this. Yeah, you can see the plot. It is okay. I showed only up to 500 in this, but you can see that below as well, up to 700 meters. But at the same time, this is the dynamics of eastern, the coastal, the just in the shelf break. But in the open ocean region, it is just reverse. So recently, the Moderator and they discussed the same feature, the seasonally dynamic of this ocean dynamics between this 12 and 15 degree. They showed up to 9 degree north, but it is just reverse. During the winter monsoon, it is towards the north, and monsoon time, it is towards the south. So that means there's a within the like a small region, there's a dynamic, the horizontal dynamics completely differ within a season. So that we need to address very carefully.
Thank you, Sudheesh. There's one more question posed in by Joey De Silva. He wants to know, can you explain the horizontal and vertical growth of OMZ and its impact on the shelf? I'll repeat that. Can you explain the horizontal and vertical growth of the OMZ and its impact on the shelf?
Of course, it is not, we cannot say the growth in the sense it is something different, but there is a vertical expansion as well as there is a horizontal expansion. Horizontal in the sense there is the expansion of this OMZ to the shelf region. So because of, so that's when this, that is mainly due to the upwelling process. When there is a thermocline shift, this open ocean, there is upliftment of OMZ, and the OMZ waters is transporting to the shelf region because of the upwelling process. So the upwelling, it is already low in water, and due to the shelf biogeochemistry as well as the runoff from the coast, it again poison, and there is an intensification of this upwelled OMZ waters in the bottom layers. So sometimes it will go even anoxic and sulfidic as well. Because of that, there is an impact on the shelf biogeochemistry as well as the shelf biology.
The third question is from Karin Limburg. Karin wants to know, can you please explain how these findings will affect India's marine carbon credit that you mentioned?
It is a tricky question, I should say. Because marine carbon credit is completely like, but we need to monitor our system very well, because when we talk about the anthropogenic input or the climatic modulations, that all will affect this marine carbon credit. So upwelling, it is a natural process, but the intensity of upwelling depends on our climate related as well as the different aspects of, for example, runoff from the land and all those things. So there will be a poisoning of this natural effect that we need to impact, that we need to monitor. Then only we can talk about the marine carbon pyramid and how this will really affect. That is what.
Thanks, Sudheesh. I'll pose in one more question to you. The next question is from Faisal Hamza. He wants to know, in terms of circulation and during the southwest monsoon, is it possible the OMZ waters from the Arabian Sea as well as the Indian Shelf or EEZ flow to Eastern Indian Ocean, that is coast of Sumatra and Java? Let me just rephrase that. In terms of circulation and during the southwest monsoon, is it possible the OMZ waters from the Arabian Sea as well as the Indian shelf to flow. So basically what he wants to know is that whether the flow of southeast monsoon water is towards the coast of Sumatra and Java.
No, it is completely our southwest monsoon pattern, and all. If you see, it is completely like from southwest to, it is southwest monsoon. So we cannot generally to, okay, understood. There is already some kind of there is a transport mechanism from south to from the Arabian Sea to the Bay of Bengal, this Indonesian region. So OMC, related to OMC, till now we don't have observations, but there are the water masses are moving from this region to that region, but that can be expected. But how much the OMZ from south to north, how much there's a oxygenation? Everything depends on that oxygenation, I feel, because there is a oxygenation from south to north through the intermediate layer.
So I basically feel he wants to know about the overall waters of low oxygen waters of the Arabian Sea, whether they are moving out towards the Eastern Indian Ocean, because he's mentioning, he's specifying coast of Sumatra and Java. They're quite down south, where we are.
As of now, to my understanding, it was not moving to those coasts, but like the in Bay of Bengal also, of course, there is a OMC and all. There is that can be, there may be a that I am not really answer to that, whether there's a movement of this OMC waters towards those regions or not. But to my knowledge, is no.
Okay, I have a question. I mean, I'm really, I mean, it's great to see the MEDA's work, because you have been able to cover the entire shelf, and you've been able to show that the work that the low oxygen that happens is seasonal. At the same time, you also have been able to point out which are the zones wherein it gets more intense, basically between the southern part around 12 degrees north to around 15 and a little bit above. And this is a zone wherein we see the suboxia happening. Sometimes in certain years, you also see the anoxia happening. And you have the observation from all along the coast. What do you feel, in your opinion, this entire thing will change in terms of from future point of view? One of the things that we would like to know from the GO2NE point of view is whether the OMZ will intensify, even though it's seasonal, whether it will intensify. If yes, I mean, what is your opinion on the intensification part, whether it will happen or not?
To me, the intensification will be there, but that might be restricted only to nearshore region, because that might happen because of the variability. That intensification also might be very short within a short span. For example, suppose if there is heavy runoff, we can see an intensification of this low oxygen in those regions for very few days or something. Because here also in our region, in the shelf region, we can see the intensified duration. The duration of intensified OMC is only maybe a month or not, or less than a month. Sometimes it is only 15 days. If you see, for example, we are seeing only during September or the end of September in the Central Arabian Sea, that sulfuric waters, but we are not seeing before that. So the intensification depends on different aspects, like monsoon rains, like the flow of rain, flow of runoff, and the different kind of production pattern within those layers and all, and also the intensification of wind. That is one of the most important aspects. Very recently, we have come across from the Afghan south, from the mudbank region. So Girish and all, they have put a Argo, not Argo, a mooring station. So very interesting results are come from that those data, and those are to be published. And what we are seeing, like it is only like within the shore or near shore, we are seeing some kind of intensification because of, but still we cannot say there is a because of the future concern there may be, that we cannot say really, because we are already seeing if there is a La Nino or El Nino condition, there's a change in pattern of this hypoxia or suboxia, that already reported in the Biogeoscience paper by Parvati et al. Last year. So that kind of variability is also mostly very much what I can say into that region. So I should say no to a certain, like in the shelf region, but can be in the nearshore region in future.
Okay. Thank you, Sudheesh. Thank you very much for an invigorating talk. It was really nice to have you. And thank you to all the people who have posed the questions. With this, Sudheesh's session ends. Sudheesh, can you please stop sharing your screen?
Thank you.
Yeah.
Thank you. Thank you.
We will move to our next speaker. That is Dr. Zouhair Lachkar. So Dr. Zouhair Lachkar is a young and vibrant researcher working as a senior scientist at the New York University, Abu Dhabi, United Arab Emirates. Zouhair did his master's in atmosphere, ocean, and environment from Paul Sabatier University, Toulouse, and PhD in environmental sciences from Pierre and Marie Curie University, Paris, France. His research interests include marine biogeochemistry, ocean circulation, climate change, marine carbon cycle, ocean modeling, oxygen minimum zones, and ocean deoxygenation. He is on the editorial board of several journals and has more than 40 publications to his credit. Today, Zouhair is going to talk to us on recent and future trends in the Arabian Sea oxygen minimum zone, processes, and uncertainties. Over to you, Zouhair.
Thank you. Thank you very much. Let me share my screen.
Yep, it's visible. Please go ahead.
Okay, thank you very much. So hi everyone, and thank you very much for the introduction. So I would like to thank also the organizers for giving me this opportunity to share my research. And I also would like to acknowledge my colleagues who have greatly contributed to this research that I'm going to present today. And finally, I would like to acknowledge New York University, Abu Dhabi for sponsoring this research. So today I'm going to talk about the Arabian Sea oxygen minimum zone and its recent and potential future evolution. But before that, let me first start by saying a few words about the motivation for addressing these issues. So the Arabian Sea oxygen minimum zone, like other OMZs in the Pacific and the Atlantic, is driven by the combination of poor ventilation in this case in the northern Indian Ocean, and the high productivity and respiration associated with major upwelling system, in our case, the upwelling along the coast of Somalia and Oman, driven by the summer Indian monsoon winds. So as was already mentioned in previous talk, the Arabian Sea oxygen minimum zone is the world's thickest and one of the most intense, and as such is considered to be a major hotspot of anaerobic respiration, probably contributing by over 20% to global pelagic denitrification. Therefore, changes in its intensity and the climate change can have consequences not only for the local marine habitat, but also for the large-scale biogeochemistry and ultimately for climate. So the ocean has already lost more than 2% of its oxygen due to warming and is expected to lose more in the future. However, deoxygenation is spatially uneven, and in regions where the OMZs are located, like in the Arabian Sea, the oxygen trends derived from available observations, as shown in the figure, are not always strong or significant. However, several recent regional observational studies have indicated an important deoxygenation, at least in the northern part of the Arabian Sea and in the upper ocean over the recent decades. For instance, on the left, you can see a compilation of oxygen profiles in the Sea of Oman. Those collected prior to 1990 are shown in yellow, whereas the more recent profiles are shown in purple. And one can see that the recent profiles are associated with shallower hypoxia and more extreme subxia at depth. The figure in the middle from another study shows the average oxygen profile of the coast of Oman for different decades. And again, you can see a tendency over time for coastal hypoxia to develop at shallower depths. And finally, the figure on the right is from a recent study that has looked, among many things, at the evolution of the nitrogen to phosphate ratios in the Northern Arabian Sea during winter time. And what you can see here is a decline in that ratio over the recent decades that indicates a potential intensification of denitrification, which would be consistent with an intensification of the OMZ. So when we look into the future, global models show a slightly different picture, with oxygen increasing in most of the Arabian Sea by the end of the century under a maximum emission scenario, with the exception of the northernmost part of the Arabian Sea, where deoxygenation is projected. I must add that these models show important discrepancies and do not always agree, even on the sign of the oxygen change. Nevertheless, this contrast between recent and future trends deserves to be explored and further investigated. So, which leads me to formulate the key questions I would like to address in this presentation. First, why do recent and future oxygen trends differ that much in the region? And in order to answer this question, we logically first need to identify the main processes that control oxygen trends in the region. And finally, what can be done to eventually enhance the robustness of those projections and reduce discrepancies among models. So as an exploration tool, I'll be using mostly regional coupled physical biogeochemical models. And as you know, dissolved oxygen levels are the result of a balance between oxygen supply and demand. Therefore, the processes that control each of the two terms of this balance will ultimately control in which direction the trend will go under climate change, whether it is deoxygenation and OMZ expansion or oxygenation and OMZ contraction. So here I listed some of these processes. I won't go through all of them. And instead, I would like to highlight that these processes can act locally or remotely on oxygen and do not necessarily operate on similar timescales. So among the processes that are acting locally that I would like to highlight a little bit more in the following slides is one, the eddy mixing and the role of eddy mixing, and two, the contribution of marginal seas to the ventilation of the Arabian Sea OMZ. So let's start with the role of eddy mixing. So many studies have already demonstrated the importance of eddy mixing for the ventilation of oxygen minimum zones in general. However, here I show some results from the work we have done on the Arabian Sea OMZ in particular. What you see here are the maps of oxygen concentration at 250 meters as simulated with the same model, a ROMS model, but using different horizontal resolutions, increasing from 1/3 of the degree on the left panel, going all the way to 1/24 of the degree on the right, which is roughly around 4 to 5 kilometers, while the lower panel shows observations or data. So the hypoxic water is shown in blue, while the suboxic core of the OMZ is indicated in purple. So as you can see, as the resolution increases and more eddies are resolved, the suboxic core shrinks, whereas the volume of the OMZ itself does not change much. And actually it expands slightly, but this involves some interesting biogeochemical feedbacks that I can elaborate on maybe more during the Q&A if need be. Also note that the agreement with observations is improved in the highest resolution model. Now, another important factor that also strongly affects the intensity of the upper OMZ that I want to touch upon here is the ventilation driven by the two marginal seas, the Red Sea and the Persian/Arabian Gulf. However, I will focus more here on the role of the Gulf on the OMZ. So to illustrate this, I show here the results from a modeling study where we analyzed the impact of closing the Gulf on the Arabian Sea OMZ. And what I'm showing here is oxygen levels along a north-south transit in the northern Arabian Sea, shown here in the map, and as simulated in the control run and a hypothetical scenario where the Gulf is closed. Note that both simulations are run at the highest resolution of 1/24th of the degree. So what you can see here is that in the absence of the Gulf ventilation, the OMZ core expands and shows substantially, as you can see on the right panel. And what is a little bit more interesting is that you don't need to close the Gulf to get such a response. Actually, we did experiments where we prescribed a warming of 2 degrees or more to the Gulf. And the OMZ core expands very similarly to the case where the Gulf is closed and becomes shallower, as shown with the colored contour lines on the left panel. So the reason for that is that as the Gulf waters become warmer, they gain buoyancy and become less prone to subduct and ventilate deeper layers in the northern Arabian Sea. So now, how does this apply to recent oxygen trends observed in the region? In order to explain these changes, we ran a hindcast simulation over the last 3 decades or so using an eddy resolving configuration of ROMs that covers the entire Indian Ocean. So during that period, important changes in the forcing have been documented, as can be seen here in the 2 upper panels. First, the northern Arabian Sea and especially the Gulf region have experienced a very fast warming, as you can see on the left panel. And second, summer winds appear to have increased slightly off the coast of Somalia over that period. Now, if you look at the model, the oxygen or the trends in oxygen in the model that you can see in the lower panel, the model reproduces the reported deoxygenation with an important decline in oxygen in the northern Arabian Sea, as you can see in the figure in the lower panel. That shows the rates of oxygen changes per decade in the layer between 100 and 1,000 meters. So next, we wanted to identify the drivers of those changes. To this end, we run additional sensitivity simulations where we slightly modified the atmospheric forcing. So in the first simulation, S1, also labeled here no warming, the heat fluxes were set to be climatological. So everything else is identical to the control. In the second simulation, the climatological heat fluxes were prescribed only over the Gulf region. So the rest is again identical to the control. This is the no Gulf warming simulation. And finally, in the third simulation, S3, the summer winds were set again to be climatological in the sense that we repeat a normal year and there is no trends in the winds, at least in the summer winds. So here I show the simulated oxygen trends derived from these 3 different simulations in addition to the control. So as you can see, in absence of surface warming, the oxygen increases in the northern Arabian Sea instead of decreasing like in the control, which indicates that the deoxygenation trends have been mostly driven by local surface warming. And interestingly, the absence of the warming, even over the Gulf region only, causes a substantial weakening of the deoxygenation trends in the northern Arabian Sea. That's suggesting that the Gulf warming and to a lesser extent, the increased summer surface winds also contribute to the simulated decline of oxygen in the region. Now, let's move on to future trends. This work was led by my colleague, Parvati, and here I will show you some of the results from this study. So here I show the projected changes in oxygen between 200 and 700 meters based on 3 different CMIP models with different representations of the Arabian Sea OMZ. So the MPI model has the closest representation of the to observations in terms of the OMZ. The GFDL model simulates a weaker and deeper OMZ. And finally, the IPSL model strongly overestimates oxygen in the Arabian Sea, and actually it has no hypoxic water in the Arabian Sea. So as you can see, the projected oxygen changes are quite different in the three models, with strong oxygenation in the MPI model, a dipole feature in the GFDL model with strong deoxygenation in the north and an important oxygenation in the south. And finally, a relatively weak oxygenation signal in the IPSL model. Now, the question is, can regional modeling improve those projections? And in particular, can we reduce the discrepancies among models using regional downscaling? So here I show the projected oxygen changes as a function of depth in the Northern Arabian Sea in the CMIP models in the left, and from regional downscale experiments in the middle and right panels. So I must mention here that we have used two methods of downscaling, where with and without correcting the biases in the model representation of present-day conditions. So as you can see, the downscaling is much more effective in reducing model discrepancies when the biases in CMIP models are corrected in an initial condition. And unlike the CMIP models, which predict conflicting trends in terms of both the sign as well as the vertical depth of the change, the downscale experiments produced a shallower and weaker, yet more robust deoxygenation. So, however, in the Southern Arabian Sea, the picture is slightly different, as the downscale experiments, even when correcting biases in the initial state, still produce different rates of oxygenation at depth with very similar patterns as those projected by the parent CMIP simulations. So the question is, why is that the case? Well, the answer is has to do with the importance of the contributions of local versus remote forcing in the northern versus the southern Arabian Sea. So Parvati has run additional sensitivity simulations to disentangle these two contributions. Here on the left panel, I show you the vertical profiles of oxygen in the northern and southern Arabian Sea in a simulation where the lateral boundary conditions were kept constant and where climate change is only experienced through the atmospheric interface. In other words, only changes in local forcing are acting on the circulation and biology. And the result is that unlike the northern Arabian Sea, where the oxygen changes are dominated by local forcing, the anomalies in the southern Arabian Sea are deeper and are more driven by remote changes through the lateral boundary conditions. Therefore, the regional downscaling is less effective at reducing model discrepancies in that region. So now when we look at the projected changes in different classes of oxygen, as shown in these three panels. So in each panel here, I show you for any given oxygen concentration, the change in the volume of water with oxygen below that threshold. So we similarly see a reduction in the model discrepancies and a more consistent OMZ contraction in the downscaled simulations, where the biases in present-day conditions were corrected. Yet some of these discrepancies persist, for example, between the IPSL model, shown with the yellow curve, and the two other models. And these are driven by differences in the basin scale oxygen distributions of the parent models, which cannot be corrected with regional downscaling. So to wrap up, I'd say that regional modeling experiments suggest that the recent observed oxygen decline in the northern Arabian Sea may have been caused by surface warming, reducing winter convection and mixing, as well as suppressing the ventilation of the upper OMZ through the Gulf water subduction. This may have caused the OMZ to intensify and shoal in the northern Arabian Sea. Now, In the future, although these same processes may further enhance the oxygenation in the Arabian Sea, global models as well as regional downscaling experiments suggest that this deoxygenation likely will be restricted to the upper OMZ of the northernmost part of the Arabian Sea, whereas an important oxygenation, probably driven by enhanced ventilation, may dominate in the central and southern Arabian Sea, causing a contraction of the OMZ there. And finally, regional downscaling of global models can partially correct some of the biases in those models that are associated with the representation of small-scale processes and marginal seas, for instance, which could lead to more consistent projections. However, at depth and close to the boundaries of those regional models, biases propagated through the lateral boundaries do persist and are not necessarily improved by downscaling. So with that, I would like to thank you all for your attention, and I'm happy to take questions. Thank you.
Thank you, Zouhair. That was a very interesting talk. I mean, it's always nice. I've always been intrigued because modeling is the future. And we had two talks, one on the observation and second on modeling. Before I have my question, I think there is a couple of questions for you in the chat box. I'll go over those one by one. And the first one is from Andreas. He's thanked you for a wonderful talk. And he wants to know, his question is, you showed that warming is key to explain the deoxygenation in the northern part of the Arabian Sea. How large is the contribution of solubility changes? Number one. Is this contribution similar to global average contribution or larger or smaller?
Yes, thank you very much for the question. So yeah, we have looked at this, and it turned out that so solubility is important really in the surface layer, the decline in solubility, but in the subsurface, in the layer between 100 and 1,000 meters that I have shown, it has to do more with the increase in stratification, because in the northern Arabian Sea, one source of ventilation, in addition to what I discussed about the role of the Gulf, is the winter convection, and so the warming, especially in winter, tends to have a very strong impact on that pathway of ventilation. So it has more to do with the reduced mixing because of enhanced stratification than solubility in the subsurface.
Okay, thank you. Second question is from Sushant Nayak. He wants to know, can you provide some information on how important is ventilation from the south in maintaining the Arabian Sea OMZ? And can it overpower the local forcing that you discussed? Very interesting question.
Yeah, thank you very much for the good question. Maybe I can show here a slide to illustrate the point here. So yes, we did some work on looking at the different sources of ventilation to the Arabian Sea. And so this is, by the way, we did it using Lagrangian particles and trying to track the water masses in the OMZ back to their sources, and we did some statistics. And yeah, it's definitely so. The southern source, of course, is dominant, as you can see here. For instance, I can show you here so if you look at just the statistics, for instance, so it's the vast majority of the water particles are connected to the southern source, much more than, let's say, what I call here local ventilation. So this is what I just mentioned before, the winter convection, etc., or even the Gulf or the Red Sea. But the thing is, it also, there is the question of the time scale at which these different sources of ventilation operate. So if you look at, and also which layer. So if you look at the deeper layers, I mean, definitely vast majority is coming from the south. This is the main source. If you look at the subsurface, and especially on short time scales, then so the contribution of the local ventilation as well as of the marginal seas becomes important. And can even be like on very short time scales, like few years, for instance, it's much more important. This is what I show here is just also the ventilation time scales associated with different sources. If you look at the panel, the lower panel. So for the southern source, of course, it takes like several decades, whereas for the Gulf, it is immediately you see the impact like within few months to 2 years. And so this is also, I think it may explain why for the trends I showed, like for the recent trends that I've looked at relatively short time period, like 30 years. So the importance of these local processes is probably more important, like the relative importance is great. But if you look at longer time scales, like the climate change time scales or the end of the century, for instance, probably the large scale ventilation, especially from the south, is probably going to be dominant. And this is, by the way, one of the explanation, or at least potential explanation, why even when we do the downscaling, it does not improve much, especially in the southern part, because it's driven by this large scale ventilation, especially from the south. So if the boundary conditions, if the parent models have issues representing this properly, that will be maintained and persist in the regional simulations. So with the regional simulations, we only can hope to improve the representation of local processes like stratification, local stratification, the Gulf, etc. But unfortunately, for those long time scales, it's really the large scale circulation that matters more. So I don't know if I have answered.
No, I think it's because in the long run, what's going to happen is one of the most important things that you want to know. So I think, and that's going to be an interesting part as modeling keeps advancing and you guys keep working more on it, we'll get more information on that. We have one more question from Andreas. He wants to know, is there a substantial impact on Arabian Sea to be expected from changes in runoff or atmospheric input via aerosols? Again, a very interesting question.
Yeah, that's a very good question. So we haven't looked at this specifically, but what I can say, I mean, runoff, I don't know, because there's, I mean, I would say that the more important, like rivers, the northern Indian Ocean tend to be more like in the Bay of Bengal. So the runoff in the Arabian Sea is relatively small, I would think. And now for the aerosol deposition, that could be an important factor, because we have done, for instance, some simulations just looking at the impact of productivity of like having dust deposition and iron supply through dust deposition. And at least with the models, we see a very strong response, very strong sensitivity to the dust deposition. So I would think that, yes, changes in dust or aerosol deposition in general could potentially have a very important role in controlling not only productivity, of course, but also the oxygen levels in the Arabian Sea.
Yeah, that'll be interesting, because I think with more warming, I think we're going to have more dry kind of situations, and continued with that will be more dust storms and all. So yes, putting that in the model and trying to look at the impact of that on the OMZ would be a real interesting thing.
Yes.
Yeah.
Yes.
So thanks a lot, Zouhair. I think thank you very much for that. With that, we have, okay, there's been, yeah, that finishes all the questions. So I would like to thank both our speakers for their wonderful presentation and for answering the questions that was posed. Zouhair, if you can please stop sharing your screen. Yeah, so we've come to the end of our webinar today, but before that, we would like to thank you again for your active participation, and we look forward to welcoming you again for the next webinar in September. Also, please check out the good news for the latest news and events in the ocean deoxygenation community. So thank you to all, and wishing you a pleasant day or night from wherever you're connected. Bye for now.